Hello, this is the last video on mass transfer concerning diffusion, and this is an example treating the evaporation of a droplet, also considering Stefan flow. First I will show you two examples. The first one is the cylinder of a reciprocating engine where fuel is injected here by this device in the center. Let me take the laser pointer. So this is an injection device. Fuel gets injected now, evaporates, and then it's ignited. The next example has gained much more attention during the last 2 years. That's the production of aerosol droplets while we speak or exhale or sneeze. And in fact, this has been identified as the main infection pathway for the COVID-19 disease. As I said, it's concerning exhalation, speaking, sneezing, and when doing an alphanumerical example later on, I will focus on the conditions that are prominent here. Now let's move on. I would first like to show you the goals of today's lecture. That's to look at the balance of a droplet, to understand what equilibrium temperature means, derive an equation for the evaporated fuel mass, or use that as we have derived it earlier, and then determine the complete evaporation time of a droplet. And for this I'll move on. Here we see here a liquid droplet. It's about evaporation, so we can safely assume that the droplet is colder than the environment. This means surface temperature is at a low value, and also the diffusion in the environment is low because the driving potential is low. Now let's have a look at what happens. We have convective heat reaching the droplet, and a small amount of mass is evaporating. So there's a remainder of heat that's available to heat up the droplet interior, and thus also heat up the droplet surface temperature. As the surface temperature gets higher, the evaporating mass flow rate increases as well, until we reach a point where the entire amount of heat delivered by convection to this droplet is consumed by the evaporation process. And this is the evaporation process is determined between the surface mass fraction and the mass fraction in the environment, and that surface mass fraction, that's influenced by the temperature of the droplet surface. Now, after that time, as I described it, we have reached this equilibrium, and this means the amount of heat equals what is consumed for evaporation, and finally the droplet temperature doesn't change anymore. Let me go to the away from the laser pointer, and this means that this is then no longer true, and that's exactly the case that I'm considering. So no heating up anymore. Droplet has reached its equilibrium temperature, and here we have a situation. We have here the liquid droplet, we have vapor or gaseous environment around, and as I told you in a previous lecture, a smart decision for this control volume is to have one boundary within the droplet and one safely outside, so we don't have to describe the process of phase change. So we have liquid entering here and vapor exiting there. Now the balance is the enthalpy flux with the vapor minus the enthalpy flux associated to the liquid has to be what is delivered by convection. Now there is no change in mass, there's just a change in phase, so we can drop here the indices for vapor and liquid and just call that m.2 primes, so surface specific mass flow rate. Sorry, oops. And this times the difference in vapor and liquid enthalpy equals the specific heat flow rate, and we can express this difference in enthalpy as delta HV, which is the enthalpy of vaporization, and Q dot convection we can express as alpha times delta T. And the temperatures that are important here, that's the free stream temperature. Let me put it here, that's just somewhere, and the surface temperature of the liquid. And we'll work now with this equation in the next few slides. So it looks like when we check this equation that it's pretty simple and easy to just change the equation to get the liquid surface extracted from the equation, like this here. However, the liquid surface temperature is also hiding in some of the parameters on the right hand side. For example, the enthalpy of vaporization is a function of the liquid temperature, as at the critical point we have no longer a value for the heat of or the enthalpy of vaporization. And for the mass flux we will also have a look at it in a few seconds. So this procedure does not work, because implicitly we have temperature of the liquid surface also included on the right hand side. So the approach does not work. Now let's have a look at m.2 primes. We already wrote it down in one of the previous videos. So that's the mass transfer coefficient times the driving potential and multiplied by 1 over this here, which is the Stefan factor. So we see here that the terms in red, that's Xi vapor at the surface, that's a function of the liquid temperature at the surface. This here is the Stefan factor, and we also have here the mass transfer coefficient, which we can determine using the Lewis law, which has been derived by the strict analogy between heat and mass transfer. And this means we can express the mass transfer coefficient by the heat transfer coefficient and then use a Nusselt correlation to determine this. Now let's go back to the equation and see how we can determine the liquid surface temperature. And for this I will just name the two terms by I and by 1 and 2 here and discuss this graphically. So I'll plot these two terms as a function of surface temperature. Now let's have a look at the first term here, the heat transfer, the amount of heat transferred. So that's the hot ambient temperature minus liquid surface temperature. In the beginning this is a low value, so I have a large difference. I would expect a larger value here. When liquid surface temperature in this diagram, for example, increases, this difference decreases. So I would expect to have a course of this graph somehow like this. The term on the left hand side, I will just discuss it for the mass flux, which is shown here on the right hand side. The nominator increases as surface temperature increases because Xi vapor at the surface increases. This is a constant value assumed for this example here. And it's divided by 1 minus something which gets larger with surface temperature, so this difference becomes smaller, and in total this value is increasing. So this term shows a behavior like that, and at the intersection we can determine the equilibrium temperature. This is done numerically in an iterative procedure, as I did not elaborate the enthalpy very much, but Xi vapor surface is a function of temperature as well, and this we can only determine it iteratively. Now let's look at evaporation time. And the question to look at is, at what time has the droplet completely evaporated? So we look at our droplet, and there is a mass flux leaving the droplet. This can be expressed as the change of mass of such a droplet is the mass flux times the surface area, and since it's decreasing I have a minus sign. Now let's elaborate this a bit further. The mass here is rho times the volume, so it's rho time, assuming rho being constant, change of volume. m.2 primes, I just wrote it down on the previous slide, that's this G times driving potential divided by the Stefan factor times surface area. Now the volume of a sphere for my droplet, that's 4 divided by 3 pi r by cubed. And this expression is often abbreviated by B, so we derive this equation over here. Let's have a closer look at that. And if we do the differentiation here, or put the 4 over 3 pi in front here, we can get rid of the pi and the 4. And if we use the chain rule here, we can get to dr over dt and get rid of r squared, and the 3 cancels out here as well. This means now liquid density divided by g times dr equals minus b times dt if I do separation of variables. Now b I have over there, g is missing. I'm determining here g from Sherwood number, and I'm assuming I have a droplet which is stagnant in the environment. This leads to a Sherwood number of 2. So that term here stems from the definition of Sherwood number, and I resolve that after for g, and I end up with the vapor density times diffusion coefficient divided by the radius of such a droplet. Now putting that into the equation, then I'm integrating from the initial diameter to some diameter here on the left hand side, and this is time t equals 0 to t. When I do the integration, I get this 1/2 r squared minus r initial squared equals minus rho vapor divided rho liquid by rho liquid times b times d times the time t. Now this can be arranged in a way to give me r squared over r initial squared, and that's then 1 minus this expression, and the dependence is r squared depends on time. I have here also the ratio of these two densities. And when I plot this in a diagram, when I name the ordinate r squared over r initial squared, I get a linear plot versus time. And of course the evaporation time is when the radius goes down to 0. So in this equation I put a 0 here, and then I resolve that for time. I have done that here. So my evaporation time is this expression on the right hand side. There's b in, there's diffusion coefficient in, initial radius squared, and the density ratio. And now let's have a look at that, also using some numerical values, focusing here on this aerosol exhalation during speaking, for example. That's the equation to look at, and now I take numerical values. The b I've taken from the previous example, the evaporation at the lake, and there's water vapor, so I've just replaced the vapor here by H2O. This was the value that can be equated with the values given there. The diffusion coefficient I assume to be 2 times 10 to the minus 5 meters squared per second. You might find slightly higher values in literature, but that's fine for the first estimation. Liquid density 1000 kilograms per cubic meter, and the vapor density here I'm estimating by the general gas equation, and I have here the vapor pressure, the specific R, and the temperature, specific gas constant, and the vapor pressure. I have used the Cox-Antoine relation. The parameters are in table 8 in the appendix of the lecture script, and I get to 2330 Newton per meter squared, 2330 Pascal. And when I put that in, R over M, the specific gas constant is something above 461. Temperature was chosen to be 20 degrees centigrade. And if I put these values in, I get for rho vapor the values shown here. If I put now everything in, I calculated for different initial diameters or radiuses, here for 1 micrometer, 10 micrometer, 100 micrometer droplets, the evaporation time. So 100 micrometer is a little bit more than the diameter of one of our hairs, and we talk here almost 6 minutes of evaporation time. Water vapor in 20 degrees centigrade environment. For 10 microns it's 3.5 seconds. For 1 micrometer diameter it's 35 milliseconds. And this is just assuming pure water. And now let's test if this very simplified equation then hits reality. for this I have taken a recent publication in Journal of Aerosol Science from colleagues from Karlsruhe University, and they have looked at water, for example, and I will compare that in a minute to another liquid that's even more important. And you see here curves, and let me put color here. So this is basically evaporation. And what they have done is they looked at a droplet that evaporates, and they fixed this droplet initially at 2 meters above ground. The droplet has a chance to settle down, and they hit the ground, and they stopped their calculation. They also did experimental verification. And that's the second part of that curve that's shown on the left hand side. This is basically here, the settling. Let me just do this again. So that's the settling. Or in simple words, if the droplet diameter exceeds that value, the droplets just settle down to the ground and are no longer there. And that's also the reason why we have these keep distance rules with COVID, because the larger droplets are assumed within 2 meters distance to hit the ground and be no longer infectious. However, what the colleagues found is the evaporation time that we have here, and that I will compare now to my own calculated values, is not the only thing to be considered in this game. See, these are the values that I just showed, and if I go into the diagram for 50 micron droplet, they have a value of about 24 seconds, for a 10 micron droplet about 1 second. The rough example showed for 10 microns we are about a factor 3.5 too high, and this value here, 100 micron, is 2 times the 50, so the correspondence time would be this value divided by 4, that's about 88 seconds. And so our model overestimates that time. But now let's look at some more realistic case, and that's about saliva. For the ones that are not native English speakers, saliva, that's the liquid in our mouth. And this saliva, I found these artifacts. Just check this again. So liquid in our mouth, that's saliva. And there the scientific colleagues found that the droplet diameter reduces due to evaporation, but due to the enzymes and other substances present in saliva, the diameter got reduced to a certain limited size, and then this droplet stayed in the air for almost forever, half an hour or even longer. And this means saliva droplets do not entirely evaporate. They stay around. And they stay around for much larger distances of 2 meters, even if you are in the ambience and wind is blowing. So that's why we have to wear a mask inside, because these droplets are present in the air that has been exhaled by people, by our colleagues maybe, or other people around us, and that's why we have to be careful here. So that was just an example to relate our droplet evaporation to something that is quite actually important for us. Now with that, I move forward to the 3 questions here. The first question that you should be able to answer yourself is, why is the determination of the surface temperature only possible iteratively? The next thing is, which considerations are behind the estimation of the evaporation time? And the last one is, why is the evaporation time of an exhaled droplet relatively large? Thank you for listening.